expected value is so important that we really need to talk about it a lot more. So just remember that expected value is the mean of the probability distribution. I wrote it right here, but a lot of students miss that and they forget it. So it's the mean, right? When you're looking at expected value, you're interested in the mean. Now, why is this so important? Well, a lot of reasons. It is the mathematical way that we use probability to determine what to expect in various situations in the long run. So this is the kind of thing that gets done with cost-benefit analysis, profit analysis, risk analysis. It's how insurance policies figure out how much they're going to charge you. It's how business ventures figure out where they're going to spend their money. It's how gamblers, professional gamblers, figure out when they should bet and when they should fold, right? Or know when to hold them, know when to fold them, to quote a famous song. Right. An actuary is actually a business professional who deals with the measurement and management of risk. So if you ever heard of actuarial tables, those are tables where insurance companies try to figure out what's the potential liability they have, what's the risk, and then what's the probabilities of those risks. Now for gambling, expected value has to do with expected profit, and that's super important as well. So, matter of fact, since it's money, I will put this in green. So we'll talk more about this in another example, but expected profit of your probability distribution, so it's the mean of your profit probability distribution, that's very important to know. So I'm just going to star all of this. This is very important stuff. All right, so let's start by looking at a risk analysis problem. We won't start with the gambling. Gambling will happen in a page or two. So we're going to look at these insurance premiums. And obviously this is a very simplified version of what a real actuarial table looks like, but you get the gist here. So we have these policies that are sold to people that are 16 to 21 years old. And these are the amounts of the nearest claim, and we're just to simplify this rounding to $2,000. So the actuarial table says 70% of the time this policy we won't have to pay out anything. 15% of the time we'll have to pay out a couple $1,000s. 8% of the time $4,000. 5% of the time, and so on. So these are the insurance claims. This is how much the insurance company has to pay out for these policies. Okay, now let's start with some review questions. Why is this a valid probability distribution? Well, it's valid because of the probabilities themselves. So if you look at the probability column, we can check, but those numbers should add up to 1. Let me go grab Desmos. 0.7 plus 0.15, 0.08, 0.05 plus 0.01 plus 0.01. Sure enough, it adds up to 1. So we know that the sum of this column is 1. So the sum of the probabilities is 1. I guess I should say P of x's is 1, right? The probabilities. And all the probabilities are not negative, right? All the probabilities are between 0 and 1. So there's no negative probabilities. Done, right? Now, why is it discrete? Well, discrete has to do not with the probabilities, but with the x. So if you want to think about it, why it's valid probability distribution, you want to look at the probabilities. This column right here, right? These are your P of x's, your probabilities. Right? But why it's discrete, you want to look to your x, right? And your x are these values over here. Let me do them in, I don't know, orange. That'll work. Here, I'll do it in orange. So x, that's this column, right? So it's discrete because the random variable, the amount of the claim, which is your x, only has 6 possibilities, right? It has 6 whole number possibilities, right? And that's it. They're rounding everything, but this is all they have. Right? No infinite decimal places are possible, right? You can't have, right? So no decimal places possible. And even if they didn't round it this much, it would still be finite because there's a list, right? no decimal places, and a finite list of outcomes. So it's kind of doubly discrete, right? If you have a finite list, finite means list of outcomes, sorry. Finite list means it doesn't go on forever, right? There's not infinite many possibilities. There's only this list, and that's it. So for this one, to figure out whether it's discrete, you have to look at the x's, right? The column on the left. All right, now we want to calculate the expected value of the distribution and determine what the expected value means in practical terms. All right, well, the expected value of the distribution is the mean, right? So the expected value is the mean of the claims, right? Because that's our x variable, is the claims. So I need to find the mean. Well, I find the mean with StatCrunch. So let me go back to StatCrunch. And I actually have this in here in the same data set. So I have the claims and the probabilities for those claims right over here. So I can go Stat, Calculators, Custom. The values are my claims, my x variable. Those are the values. The weights are my probabilities of those claims, right? Probability of the claim was the probability that went with that table. And so then I say compute, and there's the mean, and there's the standard deviation. It didn't ask me, but there it is. But all I want is the mean, right? That's what it asked for. So the mean is $1,100. It's money because, of course, the dollars were the unit for all of this. So there we have it. Now, if you want a symbol for this, this is the mean for the amount of the claim. That's what you're finding, right? Okay, now let's think here. What does this mean in practical terms? Oh, before I go any further, I should probably write the StatCrunch real quick. So we have it on the previous page, but you never know what page you're going to go to when you go to do these problems for, say, a worksheet or something. So we'll just write it down. It was Stat Calculators Custom. There we go. That's where we went, right? Where x was the values and the values is the x, and the weights are the probabilities. There you go. All right, now what does the expected value mean in practical terms? Well, what it means is that this company expects each of these policies they sell to have to pay out $1,100, right? So the company, the insurance company, expects each of these policies to cost $1,100, right? So they're selling them hoping that a child 16 to 21, I guess they're not all children. So they're hoping that a 16 to 20-year-old won't cost them a thing. That's what they're hoping for. But they're expecting, they want to plan for $1,100 a policy, at least, which gets to the next question. So how much should they charge so that they make a profit? Okay, well, if they want to break even, let's start with that. Let's suppose they don't want to make a profit. Let's suppose they just want to break even. So if you want to break even, charge $1,100 per policy, right? So they're saying, hey, we hope we have no claim. We hope that, nothing happens, right? And that no claims are needed for these cars and these auto insurance policies. But we expect it to be $1,100. So if we just charge every single one of these people $1,100, we'll be able to cover all the costs. Okay, but that, of course, is not how a company works. If they cover all the costs, but they don't pay for the employees that figured out these tables, or pay for the CEO, or paid for anybody else, then they're not going to make any kind of money, right? So to make profit, let's take a moment and remind ourselves what profit is. It's probably been a while since you've been in economics class. So profit is revenue minus the cost. That's just an established fact from economics, right? In other words, it's your gain minus your loss. There are other ways to state it, but that's getting at the heart of it, right? So it's the money in minus the money out, right? Money in minus money out. That's profit. Okay, so look, they're expecting to have money out be $1,100 per. That's what we're saying. So if they want to make profit so that they can actually run the company, they need to charge more. To make a profit, the company needs to charge more than $1,100 per policy, right? Because the money out should be $1,100. That's basically what we're figuring out. Like, hey, each of these policies is going to cost $1,100 roughly to the company. So we need to charge more than $1,100. So that way we've got ourselves covered in case there's, all of a sudden everybody starts driving worse and it's higher than we expected. And so we can cover the costs of our building and our computers and our electricity and our salaries for our employees and everything else that an insurance company needs to run. Oh, and that's what a premium is, by the way. Premium is the money that you charge. That's an insurance term for a policy, right? So it's the money you charge for a policy. I realize some of you are young and might not realize this, but that's what a premium is. It's the amount that the customer has to pay to be insured. All right, so let's suppose the company had 10,000 16 to 21-year-old customers, so which they charge an average premium of $1,500. How much profit does the company expect to make? That's a good question. Okay, so let's figure out the profit for one of these policies. So profit for one policy. Okay, well, that's a C, by the way. It looks like an O because my C grew into my Y there. Okay, well, profit is revenue minus cost. So it's revenue minus cost. So they're taking in, it's money in, which is $1,500, take away $1,100. So that's $400 per policy, per one policy. So then the profit for 10,000 policies would just be multiplying that times 10,000. So you take your $400, you multiply it by 10,000, and you have 4 followed by 1, 2, 3, 4, 5, 6. So it'd be $4 million. Oh, and I just did that in my head. That's a trick with powers of 10 that you can just take the number of zeros, but in case you don't believe me here. So 400 times 10,000. I did 100,000. 10,000. There you go. It's 4 million. So we can continue to do this all over the place. We can figure out the profit or the expected gain or loss for a single game or a single experiment, or in this case a single policy, and then we can just multiply it by however many they're going to be. We'll see that trick used again in an example, but a couple pages away.